Okay, so welcome back. So I think we are going to do something experimental now because I want to engage you a little bit more, and I have not prepared this, but we can do an exercise together, or at least see how far we get in a little bit of time, because in the interest of time, I don't want to wait a second. Maybe it's off. Oh, stupid me. Yeah, sorry. Yeah. So I will bounce off you this problem, which comes from this Dorigo experiment, which I mentioned at the beginning. This is an array of detector tanks filled with water on the ground, read out by photomultiplier tubes. And you know, sometimes there are cosmic showers of particles that come from high energy protons or photons that hit the atmosphere and produce showers, electromagnetic showers in case of photons, or also hadronic showers in the case of protons and iron nuclei or whatever they come from. And these particles hit the ground. Typically, there will be muons and electrons and photons on the ground. And in fact, muons are used to distinguish between protons that generate lots of muons and gamma showers that don't generate many muons. But the problem here is to, first of all, reconstruct the direction of a shower, the point where it hit the ground. And of course, these things come at any angle, so there will be also two angles, a polar and an azimuthal angle, that tell you where from the sky the cosmic ray seems to have come from. And then, of course, the particle also has a specific energy. The more energy, the more particles get on the ground. And so what you have at the end is a number of particles that each of these tanks detects, and also the kind, if they are electrons or muons, because these detectors can distinguish them. So the problem is a regression problem where you want to determine these 5 parameters: energy, angles, and the x and y positions of the center of this cone that impinges on your detectors. And we can make the problem a little bit easier to do a little bit of coding together if you want in a little while. Let's first consider the problem. So for our studies here, we could consider vertical showers. So they are given for granted that they come directly from the vertical. So these two angles don't matter any longer. And because your observable quantities, the number of particles that you see, depend now only on the distance that your detector is sitting at from the shower center. And of course, they will also depend on the energy, but we will assume that the energy is known. And so we can simplify everything to the bone, and the distributions of particles that you see becomes very close to a negative exponential distribution as a function of the radius. So this is dn, for instance, muons as a function of the distance. And the distance is the distance from the shower axis of the point x0, y0 of the shower, and you will have a detector sitting here at a distance r. All right? So this is the model that you can write for the flux lambda, which I wrote here as dn over dr. I wrote it as lambda because this is a Poisson measurement, because the number of particles is ultimately that you see is a random variable with a Poisson distribution. And this is the number as a function of radius. If it is a shower produced by a gamma ray, we'll have a distribution which is a negative exponential with some normalization factor, which is different from gamma showers and proton showers. And you see, with two different slope parameters, so that actually you can think of distinguishing these two distributions because they have different slope parameters and different normalizations. So this is the problem. And by the way, since this is, I plotted this as a function of radius, but if you consider now as a function of the x variable only, so you have to consider positions around in the x-axis, and this will become a distribution like this, which now has two sides because x can be lower and higher than x0. And this is a statistics distribution that you should know. Do you know what statistics distribution this is? Anybody? What? It's an exponential on both sides, but it's called the Laplace distribution. An exponential of the absolute value of x in this case. So actually, we will use it in an example also tomorrow, this particular distribution. But okay, we can try to do this setup. Assume that we have 100 detectors on the ground with positions xi and yi from I equals to 1, from 1 to 100. And we could even specify that their positions in the xy plane, let's say that this is x and this is y, and let's say that they start at 0, 0, and they are 10 meters apart from 0 to 100. So sorry, these are 11 detectors. Okay, so up to 90, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 detectors here. 1, 2, 3, 4, 5, 6, 7, up to 90 meters in x and y. So this is a reticle, a nice reticle of detectors, and so on. And this is easy to specify in a computer program, right? You loop on x and y, and you set the x and y's. And we observe a flux of particles. Let's just take muons, n in each of these detectors. Not all of them. Some of them might detect only 0 particles. And how do you simulate a shower? Well, you first have to determine the distance. You first determine a position where you want to generate your shower. And we might decide to generate showers in a larger area from, I don't know, minus 100 to 200 meters or something in x and y. You take a random point here, and then each detector, you find the radius, and this will determine the flux. And then you throw a random number, and you determine the number of particles that that detector has seen. And so you have a number of muons that each detector has seen. And this is the data generation part. And once you have generated the data, you can actually try to reconstruct it. You can write the likelihood of the observed data as a function of the position of the shower axis on this plane under the two hypotheses. But we can take just one hypothesis in this example, okay, since we just want to compute a likelihood. And the form of the likelihood function for the two parameters x0 and y0, given the number of particles observed by that detector in detector Ni, for all of the detectors that we have, 100, is, what is it? We said that these are Poisson measurements. We have 100 detectors. So this will be a product of Poisson factors, yes. A product of 100 different Poisson factors of observing Ni given lambda I, where lambda is a function of the radius that each detector has from the shower center. Okay, here are the likelihoods. Let's just think about one of them. You see that this is lambda to the n times e to the minus lambda divided by n. And each of the lambda depends on two parameters A and B. The parameters A and B, we can just fix them. We don't care because we don't want to fit for the parameters. We consider that they are fixed. We can consider that we know these two parameters. We know exactly the model. We generate data according to the model, and then we want to reconstruct the shower according to the model, but the parameters in our likelihood is the unknown position of the shower on the ground. So if you want, the likelihood will depend on R. So it will depend basically on x0 and y0, okay? And this will determine R, and this will determine the flux, and so the likelihood is a function of x0 and y0 through these lambdas. So to find the position of the shower under your hypothesis, you need to take the logarithm of the likelihood, because then this product becomes a sum of logarithms, and you derive the expression with respect to x0 and y0 in turn, and set the derivative equal to 0. And this will allow you to estimate the position of the shower. So yeah, I think we can try this. You can try this at home, but I think we can also try, since most of you have a laptop in front of you, and I think you have a root installed, we can try to do some common coding session. I will also start from scratch, and I can do it on the big board, and we can try to see how far we get. We give ourselves 20 minutes or so. Okay, let's see how far we get. But probably what we can do before in 20 minutes is not a two-dimensional problem. We can simplify it a bit better. Not 3 detectors. We can still use, we could use 10 detectors and only do a one-dimensional case where only the x coordinate counts. So we have a line of detectors, and we have a shower that hits at some point on the x-axis, so you have only one parameter. And we have these 2 shower parameters for the gammas, for instance, 10 times x to the minus 100 times the distance in x. And we can try to look at our maximum likelihood estimate for the position and compare it with the one that we generated at random. Okay, if we pull all of this off in 20 minutes, we are dragons. Okay, and solving the equation for x0 requires a computer program because it involves exponentials. Okay, let's set up to work. What we can do is to, first of all, we need to solve the likelihood as a function of x, right? So we said that the likelihood is a product of Poisson terms. And these are ni's and lambda i's that depend on x. So the logarithm of the likelihood is a sum of logarithms of e to the minus lambda times lambda to the n divided by n factorial. And so this becomes a sum of minus lambda I, because e to the minus lambda for the take the log becomes minus lambda, plus n times the logarithm of lambda minus the logarithm of n factorial. Okay? So since this is a sum of terms which we have defined as lambda I equals 10 times exp of minus 100 modulus of x, we have everything we need because the likelihood is defined as a function of x. So we can actually take the derivative of the logarithm likelihood with respect to x. And sorry, this x is in fact xi minus x0, where x0 is the shower position. Okay, so we need to determine the derivative of that likelihood with respect to x, which will be something x0, which is the shower position that we need to determine. And so this will be minus delta the lambda over the x0 plus n over lambda times the derivative of lambda over x0. And the other term doesn't count. And so we will have n divided by lambda minus 1 times the lambda over the x0. But this will be a sum over all the terms because each of these is a lambda I and an ni, okay? So we will have to code this. I don't think we can get through everything, but at least we can start. And what I suggest that you do like what I am doing. You open let's see if I can find. Okay. So I can take from previous work. I can take. Let's see if I can take a few includes that are useful for histogramming. And I take a new file. Okay, so we will call our macro shower, and we say that it's a void. Can you see the screen? So this is the function we can write. Can you see the screen? Yes. So we need to generate a shower, and we say how many showers we will generate. Okay. And so we have an array of detectors, and the positions are only on one axis. So we say a double X of 10 detectors. And we can do for I equals 0 to 10. And we generate the position so that we don't think about it any longer, right? So we can say that the position X of I is I need to define a random number generator here, like this. So this is an object called trandom3, and it allows you to generate data according to several statistical distributions. And now what I do is I do xi equals, let's say, 10 times I. Okay, so this will go from 0 to 90. You have 10 detectors now. And now we generate the data because we said that we generate 100 showers. For n showers equals 0 to n showers less than n. And n plus plus. And here we generate the showers. What does it mean to generate a shower? We have to take that model and we have to take that parameter. So we take a parameter x0, and for us the parameter true x0 will be a MyRNG call. Sorry, this is MyRNG call to a uniform between minus 100 and 190, let's say, because we have from 0 to 90 are detectors, emitters. Okay? Please tell me if I'm doing something that you might do differently. But you can look at my screen, but you can also try by yourself, huh? Because this is an exercise. Don't let me all do all the work. Okay? So think about how you would generate these showers now. I have my solutions, but I would like you to think for 30 seconds at it. We have to find a number, lambda, that depends on the distance of the shower axis x0 to the detector position x of I. And we have to do this flux calculation for each of the detectors I. So we will have a loop over all the detectors. We will find the distance from the shower axis, which we have defined, and this is true x0. And we will use our model, which is lambda equals 10 to times exp of minus 100 times that radius, the x in absolute value. And we will determine a number. Then we will throw a Poisson count with that number as the mean of the Poisson. This will give us the number of particles that we see in each detector. Questions? No questions. Everything clear? Well, I proceed, but you should do the same. And then we can compare our results. So we have to do a loop on all the detectors. So I have 10 detectors. And what do we do for each detector? We first of all compute the distance. And we do the FABs, the absolute value already, so that we don't screw up. Right? So we now have the distance of this detector from the shower center. Now we find the mean number of particles expected at that detector. And we said that our model is 10 times the exponential of minus 100, sorry, did I say minus 0.01 times, yeah, because this parameter is 0.01 because this x is measured in meters and we want to have a certain flux that goes down as we go to smaller values. Times the distance. This is the lambda, this is the mean of a Poisson. So now I want integer, but let's have a float because it's better anyways. N muons of detector I that we generated as a call to my RNG Poisson of lambda. Does it make sense to you? Yes? Yes, and SH++, and I still need to close the loop because we are generating 100 showers. And every time we generate a shower, we then want to reconstruct it. So we will have a part, but yes, thank you for that. So this is correctly an SH. So we have generated our flux in each detector for this shower. And now we can try to solve the likelihood. This will actually not be easy because I realized while I was explaining to you the problem that you don't have a means for solving quickly the problem with these logarithms. But we can get to some point anyways. So how do we reconstruct the shower position? What we need to do is to compute this log likelihood, first of all. So to compute the log likelihood, you will again have to loop over all the detectors and summing up this sum of logarithms, right? So I do double log L equals 0, first of all. Then I do 4 int idet again. Well, we said 10, so let's do 10. And inside here, we do the log likelihood plus equal to what? This is the derivative, but we still are computing the logarithm of the likelihood. And this is the sum of logarithms of the Poisson terms, okay? But these are the Poisson terms that depend on the parameter x0. So we are already in a stage where we need to take an assumption for the derivative x0. So since we don't have time to do a solution, we can just, I think we can do for today a nice thing, which is to just plot the likelihood per each of the shower and see what shape it has. So we will loop on positions over the x-axis and compute this. I think it's already something for that we can show for today. So we will assume a position x and loop on the position x. So for Ex equals 0 to Ix less than, let's say, 200 beans, and we will populate the histograms. And inside here, we compute the likelihood. And then maybe at home, you can do the rest of the exercise, which involves computing the derivative properly instead of doing the simple histogram we are doing now. So, so we can generate a TH1D, for instance, L log L profile. And I do 200 beans from minus 100 to 180, we said. So let's do actually 280 beans. And here I want to fill this histogram with the likelihood that we get. So here I will assume a certain value for the x0. So I will do double this x0. And I will say that this is Ix minus 100. So it starts at minus 100 and it goes all the way to 280. But let's add alpha meter so that it is at the center of the bin. Okay, so we now know what this x0 is, and we can compute the logarithm of the lambda. So we now need, for each detector, we need the lambda. So the lambda for this detector, first of all, we compute the distance again, but this is the distance from the assumed, not the true position. So this distance is equal, we said x of I that minus this x0. And we take the absolute value of that. And then we compute the lambda as 10, our model, times the exponential of minus 0.01 times this distance, okay? So now we have the lambda, so we can compute the Poisson term. And this is exponential of minus lambda times lambda to the observed number of counts in that detectors, which is n mu, okay? divided by factorial of n mu of I det. Now, I have the factorial somewhere in my code that I use for something else, so I will just fish it from there. But it's a very simple routine that you can write in 5 lines of code. And I put it here. So this is the factorial function. It passes an integer and it computes a factorial of n minus 1 times n. So it's recursively computing the factorial. And so we now have it, and we can divide by the factorial of n mu of I det. And this computes the likelihood for all the detectors. And what we can do with this is just fill the histogram. With the log likelihood. Now, it doesn't make any sense to loop over 100 detectors to do this, because we don't want to generate 100 histograms. So for now, let's take this parameter away. And this number of showers, for now, we comment it out. And we will just generate 1 shower and just look at how it looks like, okay? There is a problem with the parentheses, I think. So I take this 1 step in. And, oh yes, because here there's a parenthesis. So we can now do a t-canvas. I go to the t-pad and I do okay. Let's see how this works, okay? So let's look at what we have produced. We have a shower. We generate a random free. We have a random number generation, which we call my RNG. I generate 10 positions for the detectors. If you do it at home, you can do X and Y, so generate X and Y positions in a grid. Here, I'm just putting 10 detectors in a line, so it's very simple, 10 meters spaced. And then I generate 1 shower, which has a true X0, which is uniform between -100 and 190. Yes, why 100 and 280 later? Let's do 290 beams. And okay, so for each detector now, I compute the distance from that point of the shower of each detector. And this allows me to compute a flux, which is this model here. And I compute then the number of particles seen, which I can actually declare externally. As a Poisson of lambda. And then I generate a histogram and I loop over the X positions from -100 to 190 so that we can look at the likelihood as a function of the position. And I do this X0 is Ix times -1 times Ix minus 99.5. And now I reconstruct the detector likelihood by computing the detector distance from this particular X0 and find again the flux. And now I have the likelihood as a sum of, oh, sorry, this is the log of the likelihood. So I wanted to take minus lambda plus n of mu times the logarithm of lambda. Yes, thank you. Yes. I should use my glasses, which are there, but okay. I have trouble seeing. And this is log of factorial, right? And now I fill the logarithm and I plot it, okay? Let's save this file that is called try.c. I really need my glasses. We are already using 20 minutes, so let's try to see if this works now. Okay. Okay, large number is on the, what is large number here? Okay, return. And then what else? M new, 54 is just new. And then 56 missing this and IX missing. Yes. Okay. Let's see if this works. Maybe there is something else to fix, but let's try. Okay, and I can launch try.c. Why? I did not call it try. What did I call it? Oh, okay, let's call it try. So we have another error on line 30 now. Maybe try is a reserved name. So let me save this as shower. Okay, so here is your likelihood profile. I don't know why it works this way, because it looks like it's parabolic here, but then it has some weird behavior. So we'll have to fix it. I assume that when it is too far away, it generates what? Yeah, probably we have trouble with the factorial. So let's see. Anyways, let's see what position it had generated, because we want to compare the true X. So we will do cout. And then also, since we are at it, let's plot the number of muons. All right. So this was meant just as a demonstration that you can play with these things, and maybe you can use this as a skeleton to extend this later. So the true position of the shower was at 199, 89 meters. but the shower here gave only a few muons, so we should probably increase the flux, otherwise this is very hard a problem for. What I don't understand is why we are not getting any evaluation, but probably we missed something. So it's a good exercise for you to debug this. We have the positions and we can actually plot them. Where is the position x of like that? And x is coming later? No, I defined it before. So let's increase the flux model so that we get more muons. And I need to do this in 2 places. So 100 times this. And minus lambda plus n mu times log lambda. Lambda, oh, okay, lambda was, so we need to do this. Okay, I think that's all that we can do for this afternoon as a practical. Is it okay? All right, so it's very badly written code, but okay, now it's even more cryptic. But at least we bumped up the number of particles in all of the detector positions. Yeah, so there is something it could be. We should get a flux expectation of 0 there, but I think the condition you wrote here if lambda is larger than 0. Yeah, and the factorial, the number of muons is never a problem. Okay, so I will do the following. I put this piece of code in my area after this lecture, and then you can have a look at it and correct my mistake, okay? And maybe tomorrow we can see who has the best plot of a likelihood profile. But if you want, and if you like it, this evening you could actually solve the real part of the problem, which is instead of doing a stupid histogram of the likelihood, really insert these conditions, that is this condition, a sum over the detectors of these derivatives of the flux, and the derivative with respect to x0 of this is very simple to calculate, right? It's you just take this out of the exponential, you sum it up, you equate it to 0, and you solve it for x0. It's laborious. I guess it would take 1 hour of your time, but you can solve it for x0, and then you can do a loop on 1,000 showers, and you can plot the difference between the position, the true position of the shower, and the reconstructed position of the shower, divided by the uncertainty. And to do the uncertainty, we'll have to do the second derivative of the log likelihood and invert it. Sorry. And take the square root. Yeah. What we're doing here is doing the histogram of log, while we should be plotting x versus log. Oh, that's right. We are plotting the logarithm. That's very stupid. Yes, so we already have the solution. So you can try this at home, okay? But the gist of this is just that this is starting to be a real physics problem, estimating the position of a shower on the ground based on detector counts. And it's not rocket science, right? It's right at your fingertips. In a matter of an hour, you can do it. And then you can actually produce more interesting stuff than just this by this program is minimizing a position uncertainty, but okay. Let's go back to my lectures now. Yeah, because we have a few things to discuss. All right. Good, we are back. So, if you correct that mistake, and let's see how far you can go with that, okay? Let's look at the other estimator that we use in many applications, that is the chi-square. And that is the product of the method of least squares. Now, you imagine that you have a set of n independent measurements, y, that are Gaussian random variables. Now, Gaussians is important. We assume we know the distribution of these variables, okay? That, however, have a known means lambda, and you assume you also know the variance of these measurements, of these random variables. So you know that they are Gaussians, and you know what the widths of those Gaussians are. You just don't know their means. And then you can write a joint PDF for all of these random variables y with the unknown means here and the sigmas, which you know as specified parameters. And this is just a multidimensional Gaussian, as you see, the product of the normalization terms times the exponentials, okay? And let the lambda, the true values of these y random variables, a function of the x. And then you have a set of parameters that describe the lambdas, theta 1 to theta m. So all of this complicated construction is to describe the following histogram, where you have x, you have a certain number of measurements of y, and you see that these measurements of y have different values and different known variances in this case, okay? And then you have a model, and the model is a function of x. Lambda is a function of x, and it has some parameters, maybe 2 or 3 parameters. This is probably a quadratic or a cubic I overlaid to the data point. So lambda is our model. Theta are the parameters of the model. We want to estimate the parameters of the model theta given the data xy, where we know that the y's are sampled from Gaussians of known sigmas, sigma I. Okay, so this is just fitting a histogram with a model. But I wanted to take the hard way to specify the problem, okay? So this is a parameter estimation problem, point estimation if you want, and thetas are the parameters. Now, if we take the logarithm of the joint PDF, which describes the probability of observing the y's under the model, we get the log likelihood function, which is a function of the parameter theta. And since we assume that this was Gaussian distributions, well, then the logarithm of this is very easy, right? It's just a minus 1/2 times the sum of these quadratic terms. You see how easy is life if you have a Gaussian PDF. Its logarithm becomes a sum of squares, okay? And then forgetting the normalization terms, this is basically what you want to maximize. And if you maximize the log likelihood, this is just like minimizing the chi-squared, which is save a factor of 2 minus the log likelihood function. This is the definition of the chi-square for Gaussian data. The chi-squared assumes that your data are Gaussian distributed, okay? And assumes that you at least have a hunch of what the variances of these square deviations is, of the variances of the y, I mean, because you are comparing the y with the model. The model depends at the position x at which you measure the y. The model is lambda of x given theta. So this is a function of theta, and you can minimize it as a function of theta. How do you do it? You take the derivative and set it to 0, and then you find your parameters theta. So this expression has this property that it follows, it's itself a sampling distribution because it's a derived quantity of some sampled y's that are Gaussian distributed, and it behaves as what is called the chi-squared distribution, which is the ugly formula I showed to you this morning, okay? It is like this only if the function lambda, which I don't know why here it's capital, is linear in the parameters, and if it is the true form from which the y were drawn. But okay, there are a few boundary conditions, but the method is actually pretty straightforward, and it works also if the distributions are not Gaussian to some extent. It is, if you want, rather robust. In fact, it is used blindly without people thinking even that they have Gaussian certainty and distributions. But okay, it's an approximation, okay? But the chi-squared may have worse properties than a likelihood. In fact, it does if the data are not sampled from a Gaussian distribution, assumed that you know the true form of the PDFs. Because look, if you think you know the model, the PDF, and you write a likelihood because you know that the PDFs are not Gaussian, but then the model is not the one that you thought, you may incur in a worse problem than if you are actually assuming that the distributions are Gaussian. So beware, okay? The chi-square is not as good as the likelihood if you are pretty good at knowing what the PDF of your data are. Okay? So if the measurements are not independent, the joint PDF will be an n-dimensional Gaussian. And in that case, you have the trouble that you have a covariance matrix instead of a simple sigma that divides the squared term. And you will combine the squared term by doing a sum over two indices, I and j, and you will take the variate I times the covariance matrix, 1 over the covariance matrix term, times the difference between yj and lambda of xj. But this is the same, basically the same expression as this one, expanded when you have more than one dimension, okay? It's just a matrix form. Okay, so you know how to compute the chi-squared. It's nice that the chi-squared only requires you to have an unbiased estimate of the variance of a distribution or the covariance matrix to work, because it does the Gaussian approximation, okay? And this is a good property, but it's also a bad property. When people are doing chi-square fits, sometimes people also like to interpret the data that they look at, and they do what is called chi2 by I, right? You look at some data and the fit and you say, oh, okay, this looks like a good fit. Or somebody might say, oh, but there's another resonance here. What's the probability of this bump? And so on. So you can do that, and people could be starting to argue endlessly on whether this fluctuation downward is actually a poor description of the model of the background. So the chi-squared method, when you plot the data in the model, allow you somehow to infer whether the fit is a good fit or a bad fit. But you should always compute the probability of the chi-squared. How do you compute the probability of the chi-squared? Well, there's a function for it. But in fact, you could just plot the distribution of the chi-squared, which will be something like this. And for n degrees of freedom, it will have a mu, a mean equals to n. But then you will find a certain value of your chi-squared from your data. And what you will do what do you do with it? You are frequentists. So what do you ask if you want a p-value? What is the probability that I get a chi-squared value at least as bad as the one that I got? Now, bad means far from the mean. So if I have found this, what I will do is I integrate the tail of the distribution from that point to infinity. That will give me a p-value, okay? So the p-value, then you can convert it into a number of sigma, and then you can say this fluctuation causes a worsening of the model precision, and it actually has a significance of n sigma and blah, 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 okay? But chi by I is something that you can do, and it's actually instructive to compare what you estimate with what you actually find by computing probabilities and stuff. But you have to be careful, and that's something that we will look at tomorrow, that you can only do it if the data are uncorrelated. We will get to the point tomorrow of seeing what happens with correlated uncertainties when you cannot do all these kind of things by eye. It will fail, okay? In principle, if these are 1 sigma uncertainty bars around your data points, you expect that a good fit will go through the uncertainty vertical bars 68% of the time. So if you look at how many bars are intercepted by the model, you should expect that in 100 points, the model should go through 68 of them and miss about 30 of them. That is a good fit. It misses some vertical bars. That's what it's expected to do, because you want the uncertainty bars to cover 1 sigma. And so you expect that some of them will fluctuate away. Okay? That doesn't mean that the model is the right one, but it is a good fit. All right. And that's what I said here. And you see there are situations where you can still do chi by I on the difference between the model and the fit. This is a Higgs boson search where you can only see in diphoton final state or dimuon final state, where you can only see a small bump if you look very carefully. Anyways, let's go back to the properties of our estimators, because that's the focus of today. And there are problems if you don't know the properties of the estimators. Let's take the problem now of combining 3 measurements of the same quantity. We did it with 2, now let's do it with 3. Let these be counting rates with Poisson uncertainties. You have a counter, in a minute you count 100 decays, then the next you count 90, the next you count 110. What can you do? You can combine them, because you will improve your precision on the flux if you want. And these are all compatible with being the same number which is affected by Poisson fluctuations, right? What is the variance of 100? 100. So the sigma is 10. So these numbers are compatible. If they are not compatible, don't make the average of numbers that of different estimates. If they are not compatible, you will get a bogus result by combining. But okay, these are compatible. So let's make the combination. What is the combination of 3 Poisson counts? You just have to compute the average of them, right? Because you can obtain, in fact, the maximum likelihood estimate of the combination of these 3 numbers is, in fact, the mean. And you can do that, and you obtain this number. This is the average of the 3 numbers with its uncertainty. But imagine, for the sake of argument, that we are lazy and we put this data on a histogram and fit it with root. If we fit a histogram to a constant, you get the average, right? The mean value, the common value, the combination of the 3 values. Surely we would find the same answer as before, right? 90, 100, 110, what can we get? We will get 100, right? Nope. Nope. No such luck. If you do a chi-squared fit with root, it will spew out as a mean 99.33. Interesting. If you do a likelihood fit, it will return 100. So what is going on here? what is said is that the chi-squared fit does not preserve the area of a Poisson histogram. This is a Poisson distribution. These numbers are Poisson variates, and root implicitly assumes that your data have Poisson uncertainties. Poisson in the sense that their uncertainty it attaches to each point is the square root of the point itself. So 100, it knows that its uncertainty is 10. 90, it knows that the uncertainty is 9.5, and so on. And root does what is called the Neyman chi-square for the Poisson. So let's dig into this matter because it's relevant. In general, when you have a chi-squared statistic, that is what is the sum of squares weighted by the inverse variances, right? So the weights are the inverse variances of the true values. That's what they should be, because you want them to count more if they are the true variances are what play into the weight. But we don't know the variances of the true values. We have estimates of the variances. When we say 100 plus or minus 10, we are not saying that the true value of the flux is 100, and therefore the Poisson variance of 100 is 100, so the uncertainty is 10. We are saying we have measured 100, and so we estimate the variance of that number to be 100. So we don't know the true spread, we know the estimated one. And this makes a difference. So the chi-squared of Pearson's, first of all, is this one, which has the observed number of events, 100 or counts, whatever, minus the fitted number that you want to extract, divided by the variance, which is equal to the mean for a Poisson. So here I again put the common value that I want to fit for, my parameter. The Neyman chi-square is slightly different because it uses a different estimate for the variance at the denominator. And this is not the common fit value, but is the observed value of each beam. So if I observed 100 and it's a Poisson, the variance is 100, right? So I put 100 here, but it's an estimate, okay? So the Pearson's chi-square uses the best fit variances at the denominator. The Neyman chi-squares, it's a different definition, uses the individual estimated variances. They are good. They are two good estimators. They have asymptotically a chi-square distribution, consistent, display optimal properties, but they're using approximated weight. What this does is that it results in a pathology. Neither of these definitions preserves the area of the Poisson histogram in a fit. So you have seen what it means, that the constant is at the mean of the histogram of the beams or below or above. In fact, the Neyman's chi-square underestimates the area of the histogram, and the Pearson's chi-square overestimates it here. So what are you gonna do? Well, you will try a likelihood also, and the likelihood knows that the data come from a Poisson distribution, and that makes all of the difference, because if you maximize this likelihood, you will get as an estimate for the common unknown rate n, you will get the simple average. The proofs are simple. The minimum of the chi-square of Pearson's will find the common rate n. We just have to derive and set it to 0. The derivation gives this expression, which with some algebra becomes this. And finally, you get the result that the rate is the square root of the average of the squares of the beam counts. And this you can prove to yourself that it's an overestimate of the area, that is the average, if you want, of the beams. So it's a positive bias. Neyman's chi-square, if you do the same thing, you can solve for n this expression or just do some combinatorial calculus, and you get that the minimum is found for the rate is equal to the harmonic means of the inputs. You see, 1 over n is equal to 1 over k, that is the number of beams, times the sum of 1 over ni. And this is by force an underestimate of the arithmetic mean. So it's a negatively biased estimator. Also consistent, but biased, okay? Instead, if we do the minimization of the Poisson minus Poisson likelihood, taking the logarithm, setting the derivative to 0, we finally get the arithmetic mean. So the likelihood fit preserves the area, as we saw in the histogram before. And if we put it together, we can do a nice toy example with root. You could code it in an hour yourself if you wanted. You just take 100 measurement of a quantity which has a certain rate, let's say 50. And here I have plotted this random fishing of a Poisson of 50, 100 times. I fit it to a constant by minimizing in turn the chi-squared of Pearson's, the chi-squared of Neyman, and the log likelihood. What do I get with these numbers? Well, I can repeat this a gazillion times, and so I will get a very precise estimate of the bias I incur in if my measurements have a rate of 50, or 10, or 100. And then what I do is I put this together as a function of the rate. In this case, I was at 50 here. And what I plot is the result of the fit divided by the true value of the rate, which allows me to assess what the bias of the Pearson's chi-square, the Neyman's chi-square, and the likelihood. So you see that the bias, first of all, the bias does not go away when the mean is large. If people told you that the Poisson converges to the mean when the mean when the value the mean value is over 25 or so, this is often said, it's an approximation, right? It's not perfectly true. You still have a bias of about 5%, both with Neyman's or even with the Pearson's chi-square. Okay. And the other thing to note is that, yeah, the bias is very bad with Neyman's chi-square, so don't use it if you can avoid it, right? But it's also there with the Pearson's chi-square. And the standard is actually Neyman's chi-square in root, so be careful. So what we are doing when we fit a constant through a set of beams is to extract a common true value, which is unknown, okay? We fit for it. And we are combining measurements for doing this. We have Poisson measurements of the true value. Each measurement should have the same weight in the combination because it accesses the same information and it's just randomly fluctuating. But no, sometimes you give more weight to the ones that have a smaller value because their variance is also smaller, so we give a larger weight to them. And we give a smaller weight, a smaller weight to those that have fluctuated high. That is why Neyman's chi-squared underestimates the area. So the game is always the same. We must use estimates of the variance as inverse weights. And this happens many times in statistics. In this case, you see that it generates a bias. The chi-squared of Pearson's using as a common weight for all measurements, but is also an estimate. And the denominator is the fit result for the average value. And we are minimizing to find mu. So a large denominator gets privileged and we get a positive bias. So all of these methods are good, don't take me wrong. They can be used, they are consistent. But when we are in regimes where the number of counts is not large, which is, as I said, very often, we have to be careful, okay? And the likelihood does not have the approximations about the model by saying that it is a Gaussian instead of a Poisson, and the weights in the denominator. It has better properties. So whenever you can, you should use a likelihood. Okay, don't use a chi-squared because you're lazy. Just go the full bounty, full mile, and use a likelihood. And I think, but we have a little bit of time again. And so I want to jump to the next set of slides because if we get ahead of ourselves a little bit, it will not be bad. But in any case, you can find this set of slides at this link. And this is has been scratched before, but yeah, I will put it back here. Actually, a better link is if you don't have this symbol, you can do this instead. And this is Bangalore 2033. I didn't put the PDF yet. Okay, so we have 15 more minutes, if I'm not mistaken. And we can start with all right. So what we will see tomorrow, because we will just start now, is the weighted average in presence of correlations. We will go back to combining two measurements which have different variances, but there is also a correlation between them. And we will see that this makes things very, very difficult, okay? And we will have a few more notes on the maximum likelihood method. I will actually insert a little bit of dealing with this likelihood fitting of the shower example. If this evening I have a little bit of time, I will work out the solution to the problem that we were dealing with a little bit earlier. And then we will look at a real life example of choosing estimators by looking at a claim that was made in 2011 by the Opera collaboration that was looking for neutrinos shot through underground rock for 730 kilometers from the CERN CNGS beam. They observed the appearance of their neutrinos to look for tau neutrinos appearance there. And they were able also to look at the time that the neutrinos took in traveling those 730 kilometers in rock. And they found that they were faster than light in vacuum, which raised a lot of eyebrows. And we will look into that measurement, not for the sake of finding out what was wrong with the Opera measurement, because it was later found that there was a systematic uncertainty in the measurement. Well, I'll discuss it later, but just to look at estimator issues. Then we'll look at the probability of Poisson data. We will do some examples with root with a macro that will allow you to choose a model to fit the data. When you have some data, you have to decide what model describes the data better. And so we will do a little bit of model selection by using the F-test, the Fisher test. And then we will discuss confidence intervals and coverage, okay? And I think for tomorrow, this will be, I don't know, maybe we can go a little bit further. But let's look at the problem of combination of two measurements again. And consider when there are potential correlations between the measurements. So we have seen that Taylor series is what allows us to do error propagation, and it simplifies our life a lot. But when we do the method of least squares, we can have some problems from the approximations of the covariance matrix. We will see what I mean in a minute. So we consider the least square minimization of a combination of two measurements of the same physical quantity K, for which we know the covariance terms. So we have the top mass measured by CMS and the top mass measured by Atlas, and we know the variance of each, okay? And we also know that there may be some correlation, maybe some common, I don't know, PDF scale uncertainty or something that is common to the two experiments. We can examine two cases. We can add some systematic, no, not a systematic, let's just call it a common offset error. So both experiments have a wrong jet energy scale, so they underestimate the energy of the jets, and so the mass of the top quark gets to be underestimated in both detectors, something like that. Or in the second case, we will look at the two measurements when this is really a scale. In the first case, it was an offset, maybe 2 GeV. In the second case, it's a scale, 1% shift in the jet energy scale. So let's look at these two cases. We have a common scale error. So let's write the variance, the covariance matrix here of the two measurements. And we have, you see, a legitimate variance of the first measurement, sigma 1 squared, a legitimate variance of the second measurement, sigma 2 squared. But then we also add a quadratic, in quadrature, we add some offset term, sigma c. And that part is also appearing in the off-diagonal terms. So there is a correlation between the two measurements, which is this correlated part of the variance. So each measurement has its own part of the variance, and then there is a common part, which appears also in the non-diagonal terms. You should realize that this is just an ansatz. This is an hypothesis. I'm writing down how the two measurements talk to one another. It's a possibility, it's not for granted, but it's a working hypothesis, okay? So if I use this covariance matrix, what I need to do if I want to do the chi-squared combination of the two is to write the inverse of the covariance matrix. Now a 2 by 2 matrix, the inverse of a 2 by 2 matrix is D minus B minus A, C, and divide by the determinant of the matrix. And so this becomes this other form for V minus 1. You see that sigma 1 and sigma 2 have changed place, and there are some negative signs, and there's the determinant, but okay, this is just algebra, okay? I would strongly advise you to do this with paper and pencil, though. It takes half an hour, but it really, you see what's happening with the algebra, okay? This you see it on a slide, you see, oh, okay, do it. And you will see that it's not so, you will have to think and to ask questions to yourself. First of all, how to invert a 2 by 2 matrix, which you should do. You should know how to do it, but if you don't, you ask ChatGPT, right? And I do, I'm not kidding you, I do it all the time. So the chi-square then is the variate of the first term squared times the first element times plus the variance, sorry, this is the delta squared of the second term with respect to the common mean squared times this element of the covariance. And then you have twice these mixed terms that get the variate of the first and the second measurement with respect to the true value, and times sigma c. And this, you can minimize it by taking the derivative with respect to what? With respect to the common value k, which you are after, right? This I'm just doing what is written here, which you have seen before. So if we minimize, we take the derivative with respect to k, and what we find is this result for k estimate and sigma square of k estimate. Let's stop and look at this expression. Because you remember the expression of the weighted average of two measurements, right? It is exactly this one. Nothing has changed. So the introduction of a common offset error has not changed the estimate of the true value. Because what mattered was the uncorrelated part of the variance. In all these maths at the end, all the mixed term with sigma c squared dropped out of this, and the minimization produced the result that you were accustomed to before. But when we look at the sigma, we see that this is again the result that you are familiar with. Remember, the variance of the weighted average is 1 over sigma 1 squared plus 1 over sigma 2 squared, which is exactly this part here. Huh? It's just rewritten, okay? But here we have, in quadrature, we have the addition of a common offset error, sigma c squared. So it looks like it's legitimate. It looks like it's what you expected. If you have some correlation between the two measurements and the correlation is playing on as an offset, so you have an additional variation that is summed to your result. That is how you parameterize it, and it affects the common variance by adding in quadrature, but it's otherwise not a problem. So what is all this issue with the correlations after all? Yes. So this is what we were expecting, and we are fine. But let's now look at the normalization error. So in this case, let us start with this covariance matrix ansatz, where you see that similarly, I am writing the individual variances, and I'm adding in quadrature a term which depends on the measurements x1 and x2. So the larger is the measurement of CMS, the larger this term becomes. So it's a scale uncertainty, right? So it goes multiplied with the value itself. And then if we put these terms, we have to put diagonal terms here that depends on the product of the two measurements by these scale factors. Again, this is an ansatz, but it's a well-behaved covariance matrix, and many would come up with this recipe for writing it for such a problem. So if we invert this matrix, we get this rather uglier expression, not too much uglier, but there is this determinant. This is the chi-squared by doing the shift of the first term times the V11 squared plus the shift of the second times this plus the cross correlation terms. And now we proceed to minimize the chi-squared, and we get these results, which I ask you to look at. Now the mean of the two measurements is like the weighted average here, the numerator. Each measurement gets its weight as 1 over sigma 1 squared. And when you multiply by sigma 1, sigma 2 squared, this is x1 sigma 2 squared plus x2 sigma 1 squared. But okay, the weights are the same as at the numerator. But at the denominator, you have the two individual variances plus this term. And this term is added, is the addition of a quadratic term. So it's always a positive contribution to the denominator. So what this means is that this becomes smaller. So I have a common scale error, and the weighted average goes down. It doesn't go either up or down, it goes down. I'll take just 2 more minutes. And the variance of that estimate also has this ugly expression with this denominator here. Now, this is a bit strange, I would say, because at the denominator you have this that depends on how different the two estimates are. If Atlas and CMS are very far apart, this contributes quite a lot in decreasing the common estimate. So before we discuss further, let us test the simple cases. Maybe this is not the top mass. Let this be, no, I don't know, the upsilon mass or something else. So x1 is 10 with 0.5 error. x2 is 11 with 0.5 error, the individual variances. And then you have a common scale error of 20%. What do those formulas mean, if you plug them in, is that the average is 9.72. Does this annoy you or disturb you? Did you see something like that before? It's clear what is kind of strange here, right? The mean of the two values is outside of the bound of the two results. Okay. But it's pure math. I didn't do anything wrong. Okay. So what is going on? You will get to know tomorrow.
Questions?
Is there a typo?
The last term, if you
There's yes, there is. These are squared. Yes. Good spotting it. No, sorry. This is for dimensional reasons.
Yeah, dimension. Yeah, both of them should not have.
Yes, exactly. So this is x1 sigma 2 squared plus x2 sigma 1 squared. Thank you. Good spotting it. Okay, very good. So if you have questions, we can discuss them tomorrow, but I would ask you to try at least to go a little bit further with this likelihood that we were coding up. Maybe you get to show me a nice likelihood profile, which we were not able to do today. Or maybe you will be able to show me the fractional difference between the estimates divided by the square root of the variance by the Rao-Kramer-Frechet-Brown. This would be nice. That is the estimate of the standard deviation of the likelihood estimate, and this is the mean of the sorry, this is the mean of the departure from the true value that you get, or just do the difference squared. Okay, but all right, you understood what I mean. It's something that will tell us if the Rao-Kramer-Frechet bound applies to this measurement or not. Okay.